Hello and welcome to this lesson on probability. My name is Mohamed Kadam Kahe. I will present this lesson on YouTube, but you have also the PDF of the lesson on my website, which is indicated here. The outline of the lesson will be firstly to define the probability. After that, I will state its basic properties. In particular, I will introduce uniform probability and the notion of independent events. The last part of this lesson concerns conditional probability. I will present Bayes formula, total probability formula, and finally the tree of probabilities. So let's firstly define what is a probability. Given a finite set capital omega, a probability is a function denoted p from capital omega to the interval 0, 1, such that the sum over all omega within capital omega of p of omega equals 1. So if there are, for example, 3 values of omega, we should have that the sum of their probabilities should be equal 1. So this is the meaning of the sign here, the sum over all the values. For any subset A in capital omega, we define the probability of A as the probability as the sum over all omega in the subset A of P of omega. So throughout this lesson, we assume giving a finite set capital omega and a probability P on this set. Here is the common terminology used in probability theory. Capital omega, so the finite set on which the probability is defined, is called universe. So this is capital omega. An element in this set, say small omega, is called elementary event. A subset of capital omega, say subset A, is called event. In particular, the empty set is called impossible event, and the universe, capital omega, is called certain event. Moreover, for any subset A, the complementary of A is called complementary event. If we have two subsets of omega, A and B, such that their intersection is empty, then we say that these two sets are incompatible. So try to keep in mind this terminology often used in probability textbooks and lessons. We give now some simple examples of probabilities. The first one is a roll of a dice. So imagine that you have a dice here with 6 faces with some values here, say 1, 2 here, 3 until 6. So if you roll this dice, you have the universe, which be the set of possible results here, which are the integers from 1 to 6. We can take as a probability of each small omega 1 over 6. So for example, if you aim to calculate the probability that the result is event, since there are 3 event values, possible values, you will have 1 over 6 3 times, so you'll have 1/2. If you aim to calculate the probability that omega is larger than 5, it will be probability of 5 and 6, which gives 1 over 6 plus 1 over 6, and finally you get 1 over 3. So this is the first example. The second example concerns tossing a coin. Assume that you have a coin with two possible results. You have head here, and behind you have the tail. So the universe will be head or tail, and the probability of each elementary event will be 1/2. Observe that in these two cases, the sum of the probabilities over all elementary events equals 1 as requested by definition. We shall state now the basic properties of a probability. Consider two events A and B of the universe omega, capital omega. The first property says that the probability of capital omega, which is the universe, equals 1. Moreover, the probability of the empty set, that is the impossible event, equals 0. Now, the probability of the complementary of A equals 1 minus the probability of A. The third probability says that if a set A is a subset of B, then the probability of A is smaller or equal than the probability of B. Okay. Now we come to the last property here that I illustrated in this figure. Let's firstly try to draw what is the meaning of this. The probability of A may be viewed as the surface or area of A here. So this is the probability of A. Now the probability of B may also be considered as the area of B. So let's draw it in like this. So you see that in doing so, I'm drawing the intersection of A and B 2 times. So to calculate the probability of the union of A and B, you should add the probability of A and the probability of B, and you should subtract one value of the probability of the intersection A and B, since it is counted 2 times. We now remind some useful notation from the theory of sets. Consider two subsets A and B of capital omega. An event omega is within the union, an elementary event omega is within the union A and B, if and only if omega is within A or B. So the meaning of the union means or, whereas omega is within the intersection of A and B if and only if omega is within A and B. So keep this in mind, union means or, whereas the intersection means and. Two other properties very useful in probability theory. The complementary of the union of two sets equals the intersection of the complementary sets. So the union becomes intersection when we take the complementary. Similarly, the complementary of the intersection of two sets is the union of the complementary sets. So please keep in mind all these properties. We introduce now the notion of uniform probability. We say that a probability P is uniform or equiprobable on capital omega if the probability of each elementary event equals 1 divided by the cardinality, so the number of elements of capital omega. So in this case, for any event A, we have that the probability of A equals the number of elements in A divided by the number of elements in capital omega. So remind that this formula here is not true for any probability. It is true only for uniform or equiprobable probabilities. So here is an example, the roll of a dice. We have considered the universe as the number of integers from 1 and 6, and we have defined the probability of each elementary event as 1 over 6. This probability is a uniform probability. Now we consider a counterexample. Consider a rigged dice where the probability of 6 is high, for example it equals 1/2, whereas the probability of the other elementary events is 1 over 10. This probability is not uniform. So for this probability you may not apply this formula, since your probability is not uniform. Consider now two events A and B. We say that these events are independent if the probability of A, the intersection of A and B, equals the probability of A multiplied by the probability of B. We give now a counterexample in the case of a roll of a dice. So we considered this universe here and consider the uniform probability on this universe. Let A be the set of odd numbers and B the set of even numbers. Okay, we have that the probability of A equals the probability of B, which equals 1/2, but the probability of the intersection of A and B, which is the empty set, is 0. So you see that this property doesn't hold in this case. Hence, these events A and B are not independent. So the independence is a particular property. You should verify this equality here to assure that your events are independent. The last part of this lesson concerns conditional probability. It may be defined as follows. Consider an event in the universe such that the probability of B is non-zero. We define the conditional probability of an event A given B by the probability of the intersection A with B divided by the probability of B. So in order to keep in mind this formula, you may observe that the event by which we are conditioning is always in the denominator. Okay? We say in this case that this is the probability of A given B, and sometimes it is denoted as the probability with an index B, saying that we are conditioning with B of the event A. These two notations mean the same thing, the conditional probability. A very useful formula is the Bayes formula. It says that the probability of the intersection of A and B equals the probability of B multiplied by the probability of A given B. So this is immediate here from this formula. If you multiply both sides by probability of B, you get Bayes formula. We introduce now the notion of partition. We say that events B1, B2, Bn form a partition of the universe when they are pairwise disjoint and if their union equals the universe. Partition. So keep in mind that this notion of partition of a set. Here is another very useful property in probability theory called total probability formula. It may be stated as follows. Consider an event in the universe and consider B1, Bn a partition of the universe, such that the probability of each Bi is non-zero. Then in this case you may calculate the probability of any event A by calculating the probability of A, the intersection of A and B1 plus the probability of A with Bn. This may be illustrated by this figure here, in order to calculate the surface or area of the set A, you may firstly calculate this area here of the intersection of A with B1, then A with B2, A with B3, and finally A with B4. If you add all these parts, you will get the surface of A, and this is exactly what this formula says. Using now Bayes' formula, you may decompose the term here, the probability of the intersection, as the probability of B1 multiplied by the probability of A given B1. You may also apply the same formula for the last term, and you get a second formulation of the total probability formula. So please keep in mind this very useful formula. Finally, we arrive to the last slide of this lesson. I introduced the notion of conditioning tree or probability tree. In fact, the condition and situation may be represented by what is called a tree. For example, the tree I represent here corresponds to the following situation. We make a first experiment with two possible results, B or the complementary of B. So we start from the root here, and we say that we may obtain either for the first experiment here, either the result B or the complementary of B, and we put the probability of B and the probability of B, complementary of B, on the edges here. Now, knowing that the first experiment has result B, we may get either A with the conditional probability of A given B, or the complementary of A with the probability of having complementary of A given B. Similarly, knowing that the first experiment gives result B, the complementary of B, we may get either the result of the second experiment A with the conditional probability given here, or the complementary of A with the conditional probability represented here, that we put also on the corresponding edge. So this conditioning tree is very useful in some exercises. That's all for this lesson. I hope that it was clear and useful. I wish you good luck for your work on mathematics, and I hope I will see you soon for our next lesson. Goodbye.